Hello everyone, I'm Chen Junwei. My work is to extract time rates of the velocity and the pressure field from no time rates of the PIV measurement and high repetition probes. As we know, the time rates of the velocity and the pressure field are very important in locate the aeroacoustic noise, the source of the noise, and for the scientific research on turbulent flows and determine the aerodynamic loads. Traditionally, the pressure is measured pointwise on the surface of the object. Alternatively, we can calculate the pressure field from the Navier-Stokes equation, where the velocity field is acquired from PIV field, where there is the temporal and spatial derivative of the velocity field. Thus, it requires time rates of the PIV measurement. And the challenge of time rates of the PIV measurement is that the high-speed PIV systems are often expensive, and there is still limitation for the very fast PIV system. For example, the PIV system with high sensitive cameras, the upper limit of the time rates of PIV measurement of high sensitive cameras is over 0.1 meters per second, and for fast cameras is 10 meters per second. On the other hand, the probe can offer much higher sample frequency. However, the drawback of probe is that the probe signal is hard to interpret, and there is no spatial resolution. So our objective is to obtain the time rates of the velocity field and from the combination of low-speed PIV and fast probes. After that, we can integrate the pressure field. Here is a sketch of my work. Firstly, we are going to build the correlation between the PIV snapshot and the simultaneously measurement from the probe. After that, only with the real-time probe data, we can reconstruct the time rates of the velocity field and then calculate the pressure field using Navier-Stokes equation. And this method can let us do time rates of the PIV measurement with very affordable equipment, and after the correlation is built, only the probe is required. Here is several work I'm doing in the past year. The first one is optimal offline sensor positioning. Well, for this purpose, we are thinking about determine the position of probes only with the preliminary PIV test without placing the real probes. And we are going to find a suitable solution for the real probes. One natural idea is to use the entire row of the PIV field. And after that, we are thinking about using a row of velocity field from PIV masked by the correlation with between the upstream and the downstream edge of the field where the probe is placed. And here is the scatter plot of the error in the velocity reconstruction. And we found that the masked row-wise sensors has a better correlation with the original time series of probes, especially in the down left edge, because we are focusing on the best sensor positioning. And since the correlation is higher, so the masked row-wise sensors is a better solution than that one without mask. The second work is semi-supervised machine learning. It's based on the factor that PIV measurement often take more storage space and take much more computation cost comparing to the probe signals, especially for the three-dimensional measurement of the PIV. So we are thinking about to build the relation between the probe signal and the snapshot of velocity field with limited the probe signal labeled by the PIV snapshot and overabundant probe signal without the label. For this purpose, we introduce a second model to predict not the coefficients AT here, but the temporal derivative of the coefficient. And the two models are going to be constrained by the differentiation equations. And with the semi-supervised machine learning, we can see the pressure field after reconstruction has a better trajectory of the low pressure field, low and high pressure spots, and the performance has been improved by 36%. And there's a sidewalk about correcting the velocity field obtained from the PIV. And for this, we are using an advection model to propagate the velocity field or PIV to several previous and successive frames, thus generated several time series of velocity field in parallel, and then we are going to do a weighted average of the PIV of the velocity field, and this process is repeat for several times to have a better performance. The method is compared with conventional method like Savitz-Golay filter, which is going to fit the velocity field to a local polynomial, or using autoencoder, which is the combination of one encoder which is going to compress the information using deep learning and then depress it. We believe that after compressing and subtract only the useful information and then depress it to the original size of the figure, the noise is going to be removed. And the third method is PhD-based filter developed by one of my supervisor, Marco Raula. And the idea is to remove the higher POD modes because the noise is averagely separated in all POD modes, but useful information are often contained in first several POD modes. And here is a test from a three-dimensional simulation on a channel flow. The first row is the crosswise velocity from the DNS data, and the one with noisy. And then here comes the pressure field integrated from the original DNS field, the noisy field, and the pressure and the velocity field processed by different method. Here we found that our method, AMIC, has a very good projection of the low pressure and the high pressure errors, and from the chart in the right, we found AMIC is the best one in performance. Also, we test in the experiment in two-dimensional case, and we found MIC has removed almost all the flickering of the pressure field estimated. And here we don't know the exact the real pressure field from the PIV data because it's a real experiment. So we are using the residual of the temporal derivative of Navier-Stokes equation to value all the method, and the AMIC has the better performance comparing to the conventional method. And here is 3 of my work undergoing, and I'm writing papers right now, and hopefully it will be published this year. And here is an experiment which is essential for my paper. Thank you.